morning, everyone. My name is Kenna and today Kadi, Zheng, and I will be presenting our thesis titled Numerical Analysis of Flow Around a Biomimetic Undulated Foil Shape with Fluid Structure Interaction. Before we begin, we would like to make a few acknowledgements. First, to our principal advisor, Professor Onus, for his expertise and assistance on this thesis. We would also like to thank our reader, Professor Boyd, and our editor, Professor Lutz, for their feedback on our written thesis drafts. I will first discuss the objective of this thesis. Then I will describe the background and supporting theory. And finally, I will touch on a convergence study and first principles validation. After this, Kadi will describe the simulation workflow and our results. She will then finish with our conclusions and make recommendations for future work. The objective of this thesis is to evaluate the effectiveness of a biomimetic foil shape in reducing vortex-induced vibrations by altering the flow characteristics within the highly unsteady separated vortical wake. So what are vortex-induced vibrations? Vortex-induced vibrations are vibrations that are caused by oscillations in the wake region of a bluff body. A bluff body is a body that is not streamlined to the flow, such as a cylinder rather than an airfoil. The wake region of a bluff body is characterized by a large separated region. As the wake separates from the body, large vortices are made, and this process is called vortex shedding. At the right range of Reynolds numbers, the wake can become unstable, leading to the formation of alternating vortices. This is called the von Karman vortex street, which can be seen in the image above. The shed vortices cause pressure differences that can cause the bluff body to oscillate perpendicular to the direction of the flow, as indicated by the red arrows. We are trying to reduce vortex-induced vibrations because VIV is a major culprit in structural fatigue failure. These vibrations can have amplitudes that are greater than the diameter of the body causing them. Next, let's take a look at some non-dimensional values that are essential to our analysis. First, the Reynolds number. The Reynolds number is a non-dimensional value that describes whether the flow is laminar or turbulent, and it is the ratio of inertial forces to viscous forces. Next, the Strouhal number is used to characterize vortex shedding. It is the ratio of inertial forces due to the local flow acceleration to the inertial forces due to the convective flow acceleration. For cylindrical bodies between Reynolds numbers of 100 and 10,000, the Strouhal number should be between 0.18 and 0.22. However, it is important to note that the shape of the object will impact the vortex shedding frequency. Here we have a bluff body, in this case an ellipse. It's fully immersed in a fluid with velocity u and diameter d. Lift is the force perpendicular to the direction of the flow, and in a symmetrical body like this ellipse, the pressure distribution is symmetrical, and theoretically the lift force would be zero. But in practice, we will see very small lift forces develop due to the vortex-induced vibrations. Drag is the force parallel to the direction of flow. For an example, an airfoil shape will produce a lot of lift with very little drag, but this bluff body here will produce a lot of drag with very little lift. While the lift and drag forces themselves are useful for many engineering problems, in this case, we want to be able to compare different geometries. So the lift and drag coefficients are used. These coefficients are shown above and are non-dimensionalized by dividing the force by 1/2 times the water density times the fluid velocity squared times a characteristic cross-sectional area. So what type of shapes are we investigating? We're investigating a biomimetic foil shape. Biomimetics is the emulation of models, systems, and elements of nature for the purpose of solving complex human problems. On the right above me is a harbor seal, and this is his whisker. The harbor seal has a unique undulated elliptically shaped whisker, and the shape has been found to reduce vortex-induced vibrations. The vortex-induced vibration reduction on the whisker is beneficial to the seal because as the seal swims through the water, the whisker does not vibrate. In turn, the seal can better detect smaller disturbances in the water and hunt for fish more effectively. Work on this subject is relatively recent and largely unstudied. Hank et al. In 2020 sampled harbor seal whiskers and measured them to create an average geometric model. He defined 7 key geometric features that can be used to adequately describe the geometry. The image on the right shows a base harbor seal whisker at several different orientations. The basic shape of the whisker is that it's comprised of 2 differently sized ellipses, evenly spaced along the length. In this case, the geometric average does not include the geometry of a tapered end. M is the distance between the ellipses. A and B are the major and minor radii, respectively, of one of the ellipses. K and L are the major and minor radii, respectively, of the other ellipse. And rather than having the ellipses oriented parallel to the flow, They're slightly angled. Alpha and beta are these angles between the ellipses orientations and the incident flow direction. Continuing upon Hank's work, Lyons et al., using a numerical analysis, determined that alpha and beta were not relevant to the vortex shedding characteristics. Additionally, using the original 7 geometric parameters, they developed 4 non-dimensional parameters, which we will be using in this study. The variables are gamma, lambda, a sub t, and a sub c. To further break down these geometric parameters, we're going to start with t. T is the average thickness of the minor axes of the ellipses. T is perpendicular to the direction of fluid flow, and in this case will remain constant through the entire geometric analysis. Next, we have C. C is the average length of the whisker parallel to the fluid direction, and it's the major axes of the ellipse. Gamma is considered the cross-sectional aspect ratio, and it is defined as C divided by T. Next, lambda prime is the distance between 2 of the same ellipses. Lambda, the wavelength, is then defined as by non-dimensionalizing lambda prime by T. A prime sub T is the distance between the larger and smaller ellipses in the side view, and A sub T, the transverse amplitude, is taking A prime sub T and non-dimensionalizing it. Similarly, we have A prime sub C, which is the distance between the larger and smaller ellipses in the top view. This is then non-dimensionalized to turn into A sub C, or the streamwise amplitude. Most recently, Zheng et al. In 2023 found that the material properties of the seal whisker, including Young's modulus, Poisson's ratio, and the density. These material properties will be discussed later. Using the 4 non-dimensional parameters, a test matrix was developed. The above table is taken from Lyons et al. And describes the values for 3 conditions. The baseline condition, or 0, are the parameters taken from the average values from Hank's analysis. The high, 1, and low, -1, are used to define extreme points in the geometry. For example, on the right are the 3 geometries for A sub t. In the -1 case to the left, you can see very little difference between the 2 ellipses, and in the 1 case on the right, you can see a very large difference between the ellipses. On the right is our planned testing matrix. We will be testing each of the 4 non-dimensional parameters at 3 distinct points to characterize trends between the geometric parameters and vortex-induced vibration development. Along the top are the 4 geometric parameters. The first 11 runs are using a rigid test piece. First, we ran a smooth cylinder and then a smooth simple ellipse, followed the baseline whisker. And this was characterized by using the baseline value, the zeros, for all 4 geometric parameters. Then the next 11 runs are using the same geometries, but with a flexible structure rather than a rigid one. And run 18 finished this morning with recent runs averaging about 8 hours. To test these geometries, we're using computational fluid dynamics, or CFD. But what is CFD? CFD is a numerical method used to solve complex fluid flows. We use CFD because it's attractive in early design. It's immensely cheaper to analyze, compare, and optimize designs instead of physically testing all of the designs. Computational fluid dynamics relies on mathematical equations to solve these complex fluid flows. The Navier-Stokes equations are the governing equations for CFD, comprised of the continuity equation and the linear momentum equation. The continuity equation states that mass is conserved across the boundaries, meaning that mass is neither created or destroyed in the solving process. The linear momentum equation states that momentum within the area being analyzed is conserved. When picking a turbulence model, we had originally used a Reynolds average Navier-Stokes, or RANS. RANS is a time average solution that was deemed inadequate because it averages the fluid velocities and pressures in the wake. This makes it difficult or even impossible to study the large scale vortical flow features. So the turbulence model was chosen as LES, large eddy simulation. LES is better suited for this application because it solves for the large eddies, and it is able to capture the vorticity that's important to our thesis. The fluid for this problem is an incompressible liquid water. Since the fluid is assumed incompressible, the continuity equation simplifies to this, meaning that the density is not changing. Fluid structure interaction, or FSI, is the multi-physics interaction of fluid flow with a solid structure. FSI can either be classified as one-way or two-way coupled. In a one-way coupled simulation, information is only passed from the fluid to the structure. This method is acceptable for a rigid body in a compressible flow, like something like air. In a two-way coupled solution, information is passed from the fluid to the structure and then from the structure back to the fluid. This is better suited for a flexible structure in an incompressible flow as we have with the whisker. Another term used to describe FSI is strong or weak coupling. With a weak coupling, a full CFD run is completed, and then the pressure distribution is transferred and a full finite element analysis is run. In strong coupling, the two are iterated together, happening at each time step that CFD solves, then the FEA solves. This is more ideal for unsteady scenarios. Finally, scenarios can be steady or unsteady. In steady cases, the deformation does not change with time. And in unsteady cases, this deformation changes with time and wake oscillations and vortex shedding can be observed. Additionally, the mesh in an FSI run needs to move with the structure as it deforms. A convergence study was done at the beginning of our analysis to define our domain. There are three types of convergence that we're looking for: geometric, time, and mesh. A convergence study tunes the input parameters so that the results of each type of convergence approach a single value. Part of the convergence study is a trade-off analysis between increasingly accurate results and ever-increasing computational cost. We're looking for the best possible answer with the least time invested to compute the result. In the image above is an example domain, where D is the diameter of the circle. The upstream and outward extents are defined by the diameter multiplied by a domain multiplier x. The downstream distance is defined by 3 times the diameter of the circle times the variable x. To perform a geometric domain convergence, the variable x was changed until the drag coefficient converged. X was tested between 5 and 22.5. On the plot above, the x-axis is this domain multiplier, and the y-axis is the time average drag coefficient. We have chosen to model the domain with x as 17.5 because it's the smallest domain that can be used within the converged region. The drag coefficient of the domain multiplier here is 0.98. Shown above is the empirical data for a two-dimensional drag coefficient of a circle. On the x-axis is Reynolds number, and on the y-axis is the drag coefficient. Note this is a log-log scale. At a Reynolds number of 160, which is what we were using for our analysis, the drag coefficient should be just above 1. As you can recall from the previous slide, we found a value of 0.98. This is considered acceptable, and the first principles are deemed validated. A time convergence is checked by ensuring that the residual plots do not diverge. Here is an example of a residual plot. Residuals show the difference between the expected solution from physics and the actual result that the CFD computes. As a rule of thumb, the lower residual, the better the result. After a brief ramp-up period, the values should decrease and converge on a value as they do here. Part of the CFD setup includes creating a mesh. To create the mesh, the geometry is broken into finite pieces called cells. Each cell takes inlet conditions and solves the Navier-Stokes equations to find outlet conditions. At each time step, every cell in the entire mesh does this. The cells then pass their outlet conditions to the next adjacent cell in the mesh to use as the inlet conditions for that cell. This is repeated for each time step in the simulation. However, more important than the mesh creation is adequate refinement of the mesh. Because the response we are trying to capture is related to the wake flow, or the wake region of the flow, a wake refinement was implemented. In the image here is an example of a 2D polyhedral mesh with a circular bluff body. The wake of this mesh does not have a wake refinement, and you can see this with the large cells in the red box. Now, the mesh includes a wake refinement, and as you can see, the cells became much smaller in this region, and this allows us to pick up more information and better analyze our results. I will now pass the presentation off to Kadi, who will continue discussing the CFD workflow.
Thank you, Kenna. I will begin by describing the software used for this thesis. The commercial CFD software Siemens STAR-CCM Plus was chosen for its ability to integrate finite element analysis, or FEA, within the program. Using STAR-CCM to simulate both the fluid and the solid domains simplifies the workflow because all processes can be run using the same program. Other workflows may choose to use STAR-CCM to simulate the fluid domain and an external FEA package to simulate the stresses inside the structure. Additional STAR-CCM capabilities include integrated preprocessing for geometry creation, automated meshing, and some post-processing capabilities that are useful for examining the results. Now, I will go through the geometry creation. The whisker geometries, as described earlier, were modeled using the CAD program Rhinoceros 7. The test model is comprised of 2 undulated sections stacked together, though a real whisker would have more segments. The number of segments was limited to keep runtime reasonable. The image on the right shows an example whisker test piece within the fluid domain. An arrow indicates the flow direction. It is important to note the orientation of the whisker in the flow. Since the whisker is elliptical, we had to choose an orientation. For consistency, we tested it with a smaller axis perpendicular to the free stream. Additionally, the bottom of the whisker is fixed to the fluid domain, and the tip is free to move, which will be important during the FSI runs. Now, I will explain the physics model setup. The fluid used in the simulation is water. For simplicity, we chose the standard STAR-CCM liquid water density and dynamic viscosity. The images on the right show water flowing over a foil in the direction indicated. The top image shows a no-slip wall condition where the velocity of the fluid domain boundary is 0. The bottom image shows a slip wall condition where the fluid flow proceeds without interacting with the boundary. Although a non-slip wall would be more similar to the condition of a whisker on a seal, in our test runs, we found that the non-slip wall condition took nearly 4 times as long to run the simulation as with the slip wall. To simulate 1.5 seconds of physical time, cases with the no-slip wall took over 100 hours, while similar cases with a slip wall took 24 to 30 hours each. Therefore, to be able to finish the entire test matrix within a reasonable time, we chose to use the slip wall to simulate the fluid domain near the whisker. Lastly, coupled flow, which solves the governing equation simultaneously across the fluid domain, was used because it can resolve complex flows. The alternative is segregated flow, which solves the governing equations separately for each variable and is faster but may not represent the flow accurately enough for our analysis. Next, a major addition to the standard CFD simulation for FSI setup are object interfaces. We wish to examine the interaction between the solid whisker and the fluid, which requires us to define a fluid-solid interface between the 2 domains. The mesh in the fluid-solid interface area was defined as a mapped contact interface in STAR-CCM. A mapped contact interface does not require the exact same mesh resolutions on both surfaces, which allows some flexibility when defining the mesh cell sizes. In a 2-way coupled FSI simulation, the consistency of kinematics and forces stipulates that the corresponding fluid and solid particles at the coupled interface move with the same kinematics, that is, the same position, velocity, and acceleration, and that they experience the same forces. The 2-way coupled mesh adheres to the consistency of kinematics and forces. The mesh allows fluid to exert force on the structure, and the structure, in turn, can exert force on the fluid. Lastly, the mesh in an FSI simulation is set to the morphing condition, which allows the mesh to move and reform itself as the structure moves. For both the FSI and the standard cases, additional inputs to the program were then defined. The seal whisker structural parameters found by Lyons et al. Were used in the Thesis to model the flexible seal whisker. The seal whisker has Young's modulus of 6 gigapascals, a Poisson's ratio of 0.4, and density of 1,300 kilograms per meters cubed. For reference, the material properties of steel are shown. The whisker has a much lower Young's modulus, so it is much more flexible than steel, and the whisker is also several times less dense than steel. I will now discuss the results of our analysis. This graphic shows the rigid extruded circular model. The flow is to the right. This is a cut taken through the center of the model and shows alternating bands of higher and lower velocity in the flow, which correlates with the oscillating flow that we will observe in the section view. This graphic shows the flexible cylindrical model from the FSI analysis. Flow is to the right. The internal mesh stress is shown on the scale. This internal stress plot is realistic because the model shows stress concentrations or areas of higher and lower stress at the base of the whisker, where the whisker's movement is constrained. These graphics both show vorticity plots of the same extruded circle geometry. The difference is that the figure on the left shows the rigid case, and the figure on the right shows the flexible FSI case. The FSI case shows much greater oscillations in the vortical wake. These increased oscillations can be attributed to the response of the whisker to the fluid forces. The whisker's motion would have exacerbated the fluid's motion. For this comparison, we are looking at the FSI extruded circle condition on the left and the FSI extruded ellipse condition on the right. The ellipse displays much less oscillation in the wake condition, in the wake region, than the circle. The whisker shape, which is not shown here, looks very similar to the FSI extruded ellipse. However, we will see that the whisker shape does have a significant change in displacement due to lift as compared to the ellipse. This is a comparison between the FSI extruded ellipse and base whisker shapes. The table on the left shows the maximum displacement of the whisker free end from its original position. This displacement, which is caused by and in the direction of the lift force, is measured perpendicular to the direction of flow. The plot on the right represents displacement of the whisker free end over a period of time. The plot shows that the displacement of the circle has the largest amplitude, followed by the amplitude of the extruded ellipse, and the base whisker model has the smallest amplitude. The base whisker model is nearly a straight line at this scale, and its maximum displacement, as seen in the table, is 2 orders of magnitude smaller than that of the extruded ellipse. This comparison shows the effect of the variable gamma. The scale on this plot was chosen to display the base whisker and the low and high conditions of the variable gamma. It is hard to see the difference between the 0 and 1 cases. However, the values on the left show that the maximum displacement of the high gamma condition is 2 orders of magnitude smaller than that of the base whisker. This data suggests that as gamma increases, the amplitude of Y displacement decreases. From our analysis, we have drawn some conclusions. The first is that the rigid and the flexible FSI simulations are valid. This is because the drag coefficient for the circular model corresponds to empirical values of drag. Additionally, the whiskers stress models show stress concentrations in the expected areas, which indicates that the solid stress model is realistic. Next, when comparing FSI rigid and FSI geometries, there is more visible oscillatory motion in the FSI cases. As for the geometry, we have found that the whisker shape reduces transverse displacement as compared to the extruded circle and the extruded ellipse cases. We have also found that as gamma increases, the vortex-induced vibrations tend to decrease. The test cases with the remaining variables are still being investigated, and results will be included in the thesis report. We have some recommendations for future work. First, we recommend that the rigid and compliant structures be tested physically to compare with the CFD. One possible limitation is that While the whisker can be accurately modeled at such small scales in CFD, the scale is comparable to a human hair and would be very difficult to model in a flow channel. The geometry could also be adjusted to be more realistic to a harbor seal's whisker. This would include a tapered end and could use more undulated segments in a longer whisker shape. However, this would increase computation time. Another recommendation is to test flow in other incident directions. While we tested flow perpendicular to the minor axes, the whisker could be turned to test flow in other directions. Lastly, a larger sample size could be used to investigate the changes of resistance between the high and low values of the test samples. Thank you all for listening, and at this time, I would like to invite Kenna and Evan back up to answer any questions.